Welcome to 3.5 Inverse Relations. I'm just going to quickly give you all the good stuff. What are inverse relations? That is when in a function, I'll give you three sort of definitions for it. Number one is you switch the x and the y values. Switch x and y values. So if in the original, that's supposed to spell original, in the original function, let's say 2 comma 3 was one of the points. Now in the inverse function, guess what happens? The point would be 3 comma 2. You would just switch those, okay? Another thing you'll notice is that the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse because the x and the y values switch. Okay, now the second way of defining what an inverse relationship is, it is a reflection. Up until now, our reflections have been over the x-axis, over the y-axis, but this one is a reflection over a particular line over y is equal to x. And regardless if you think of this as the first definition or as our new definition, you actually get the same thing. So if I very quickly say, okay, I'll draw all four quadrants here. Y equals x looks like this, right? So 2 comma 3, okay, so 2 comma 3, maybe up here, right? That would reflect it, and it kind of makes sense that 3 comma 2 is over here. So this would be our original and our image. Maybe the reflection isn't perfect for my little sketch here, but it's the same idea as I was saying before. If this is like a blob of wet ink and you're folding it along this line, that's where the image shows up. And the third one, in terms of notation, if we call our original one f of x, then our inverse, the way to state it is like this: f, the inverse of f of x. You put a little -1 up there, and that's to show that it is inverse. So those are our three different ways of looking at it. Let's do a little bit of a get started here, solve each equation for x. Right now it's solve for y, isn't it? So we need to switch this around to solve for x. So what do we do so that at the end of the day it looks like x equals something? So I guess we would add 4 to both sides. So we get y plus 4 is equal to 3x. And then we divide both sides by 3. And then we could get x is equal to, well, I could say y plus 4 all over 3, or another way I could talk about this is I could say x is equal to 1/3 y plus 4/3, either way. Okay. So basically what we have found is how to find the inverse, and that's sort of like the first step in finding the inverse mathematically. So that was 1, 2, 3. That was really the switch the x and the y values, and we'll show you how this turns into it mathematically. I'm going to go over and graph y equals 3x minus 4. So if I go to Desmos here is y is equal to 3x over 4, and we've got 1 point there, 0 comma -4. So what we're going to do is, here's y equals x, and I made it a dashed line because I'm going to be folding it over that line. So we should anticipate that if this is 0 comma 4, oh, actually, you know what, I won't do it that way, that we should be getting a point at, if we switch x and y, at -4 comma 0. So let me try that, -4 comma 0. So there's one point that we'll probably have on our inverse function, and 2 comma 2, if we switch that, it'll be the same, won't it? So we should get a line that's going to cross through this point and through that point and keep on going. There's a neat way we can do this in Desmos. We can actually switch the x and the y. So where I see y, I'm going to write an x. So in the original function was y is equal to 3x minus 4. I'm going to say x is equal to 3y minus 4. And there we have our inverse function. X is equal to 3y minus 4. Kind of works nicely. The only thing about the x equals 3y minus 4 is that is not usually the way that we write our equation. So if I was to say, if this question was slightly different and it says find the inverse of this function, if I was to say x is equal to 3y minus 4, usually you want it stated in terms of y is equal to solve for y. So that's why this get started I go back to my y is equal to, what was it, 1/3 x plus 4/3. This would be how I would state my answer for finding the inverse. So if this was the question of find the inverse of this function, this would be my answer. If the question said f of x is equal to that, my first step would be to change my f of x to a y, switch the x and the y, and at the end here state clearly that what I have found is the inverse of the original function is equal to 1/3 x plus 4/3. So that is a good part of our beginning of our lesson. Let's take a look. The construct your understanding is going to be talking about reflecting this y is equal to f of x. And I think on the next page, do they answer? Do they complete the check? No, they don't. Okay. Well, let's do this. Let's do this one ourselves here. If we were to try to find the reflection across y equals x, I guess what I would do first is say, well, let's draw that y equals x reflection. So if I start here, and there you go. That is y is equal to x. Now if I was to take my original function and were to try to do a reflection of it, first of all, if there's a point that intersects with y equals x, that if you switch that value, I guess that's 4, 4. If you switch 4 and 4, it still stays at the same spot, doesn't it? This spot here is 2, 0. So the reflection is going to be 0, 2. So you see my line is going to be over there. I'll draw a line. Make it solid, maybe red. So this will be our reflection, and the reflection is going to go through this spot and through that spot. But I should try to extend it both directions. So there is my reflection. So the reflection is the inverse. So if this was y is equal to f of x, I should label this one as y is equal to the inverse of f of x. Oops, -1 up there. F of x. So that's how I would label it. That's how you find the inverse of each of those functions. This gets a little bit harder for those ones. Why don't we try this bottom one here that looks like a root x that's been moved over left a couple times. I'm going to use the exact same method. So first I guess I should get my dashed line out again, and try again. I should get my dashed line out, and I'm going to reflect across that. So if there's any points that are right on y equals x, it's going to stay there. This point here is -2, 0. So on my reflection, I'm going to get 0, -2. I'm going to get this spot here. So this is on the original function. This is on the image. It's over there. And already we can just sort of see the general shape. Let's try this one as well. This has an x value of 7 and a y value of 3. So on my image graph, on the inverse, I'll get 3, 7. So 3, 7 would be up over there. So I'll label that 3, 7. Now we just sketch it in as much as we can. So I'll draw it. Try again. Okay, I'll try to kind of like that. All right, and it does have an arrow at the end. So that's that basic shape to it. Okay, so it's a little bit... You'll get the hang of it after a while doing those inverses. It's different than a reflection across the x or the y. Now we're reflecting across y is equal to x. So those are our two kind of warm-up questions. Here they're doing an example where they made a table of values, right? And on the 2x plus 1, they picked 3 of them, and they just switched the x and the y values, got 3 points, and did a sketch. Here's our definition. Reflecting in the y equals x. For a function y is equal to f of x, the graph of, see what they do is they switch the x and the y, is the image after reflection of y equals x, and these two are inverses of each other. And this is and the important part here is that this is the notation to say the inverse of x. So this is the inverse of my original function, f inverse of x. So if this is our original function, f of x, here's the f inverse of x. And how do you do this mathematically? Well, let's just do this one as an example. Step 1 would be to if it is defined as f of x, I would change that to a y. So do a y is equal to 2x plus 4. Step 2, switch the x's and the y's. So now I'm going to say x is equal to 2y plus 4. So already this was the original, now this is the inverse. So from now on we're working with the inverse. Step 3 is solve for y. So if we're going to solve for y, it's going to be subtract 4 from both sides is equal to 2y, and then divide both sides by 2, so I'll get y is equal to x minus 4 all over 2, so y is equal to 1 half x minus 4 divided by 2 is 2. So, and don't forget the last step. This looks the same as our original function, and we need to differentiate between the fact that the original function was f of x and we want f inverse of x. So make sure you do this last step and say f inverse of x is equal to, instead of y, say f inverse of x. So everything else here stays the same, 1 half x minus 2. Okay, so this is the, make sure you got that. It's a good important stuff. And like I said, this is exactly the same result as taking all the x and the y values and switching them. Example number 1. Sketch the inverse of a function given its graph. So we got 1, 2, 3, 4 dots. For each one, figure out the x and the y values, figure out the inverse of each one. Okay, I will let you try the check your understanding here, and I'm going to stop and save this quick video. Ah, no? What did I do?